All right, so we are going to go over note 16 in CS70. This one is about variance and a little bit about covariance and some other things. Okay, so to start off, functions of random variables. So let's just define this random variable x. It's going to be on some sample space omega, and its probability distribution is denoted by this. And then we're going to have some function f, which is going to be on the range of x. That is, it's going to take in the values that x can map out to, on that set of real numbers. And f of x is going to be a random variable that we define as y, which is also going to occupy the same sample space, capital omega. So if we apply y to some sample point in omega, it's going to be like we apply the sample point to x, and then we apply that to f. So, what is the expected, or what is the probability distribution of y? Well, it's going to look something like this. So, essentially what this is saying is for all x's such that f of x yields y, we're going to grab the probability of that event with respect to x, and then we're going to sum all of those up, all of the ones that give us a y for the sample point x, and that is going to give us the probability of the event lowercase y for the overarching random variable capital Y. So this probably says it in a more succinct way. The probability distribution of capital Y for a given lowercase y in the range of capital X is equal to the sum of the probabilities of all x's in the sample space, such that f of x is equal to y. Okay. So let's see. If we want to find the expected value of y, we can just apply the expected value definition, and basically we're going to take some y in the set of some event lowercase y out of our random variable uppercase y. We're going to multiply that by the probability of that event, and we're going to sum it up for all possible y's that we have that are in our overarching random variable y. And this is going to be, if we just kind of sub in this for this, it's going to be equal to this. And as we sort of talked about in the previous video, the third expression follows from the fact that we're basically summing up all of the x's that yield a certain y. And we're going to multiply it by y, and we just do that for all the y's. But we could also just find all of the probabilities for each x and multiply that by its corresponding y, or f of x. So if that didn't make sense, maybe read, I feel like this says it a bit more succinctly. And this is also called like the law of the unconscious statistician. Now we're going to move on to talking about variance and covariance. Really, this is just kind of like the motivation behind why we need to know these two things. So let's say P is equal to the probability of landing on heads. We have n tosses. That means the expected value is n times P. For example, if we have a fair coin, n is equal to 4. The probability of landing on heads is 1 over 2. That means we would expect 2 heads in our final output of 4 tosses. So given that we have tossed the coin n times, we could potentially end up with anywhere from 0 to n heads. Right. So given our particular outcome, how do we determine how far off from the expected value we are? That's where variance and covariance comes in. So we're going to use this particle analogy to talk about sort of a walk. And this particle is going to sit on a number line, and it's going to start at 0, and it can either move in the +1 direction or the -1 direction. And each movement is independent of another movement. And we're going to define S sub n as the position of the particle after n moves. So all of these, so this is the random variable. All of these are the sort of like sub-events, so the position of the particle after one move, after two moves, after n moves, right? So if we just take an arbitrary position of the particle at some move I, we can see that by the definition of expectation, has a 1/2 chance moving to the right, plus it has a 1/2 chance of moving to the left. So its expected value is to just like not move at that point. And using linearity of expectation, we can simply apply the expectation to each term in this sum. And if we just sum up a bunch of zeros, we're going to get 0. So that's kind of what that comes out to. But something they sort of slide in is that we want to know the distance from 0, but the absolute value is hard to compute, so we're just going to get the square. Okay, cool. So now we're going to get the square of s of n, and we're going to show that it's equal to n. Okay, so if we square s of n, again, s of n is defined as the summation of from I is equal to 1 to n of x sub I. So we can simply just square this sum, and we're going to get something of the form like this. And if you don't believe that this huge string of the sums of terms squared takes on this form, then I would encourage you to draw out 3x3 example, like a 2D matrix kind of thing, and just like just do the multiplication and see how it comes out like this. Okay, so our expected, so this equation takes this form. So now what we have to find is the expected value of x sub I squared and x sub I times x sub j. So let's look at each of these separately. In our case, x sub I squared will always be positive 1, right? Because x sub I can either be 1 or can either be negative 1. That x sub I is just the the event of either of moving, essentially. So if we just plug it into the expectation, or we try to get the expectation of x sub I squared, we're going to get, okay, the expectation of moving to the left squared is, or I guess moving to the left squared is half, and then same for the right, but since it's squared, it's 1, so half plus half is 1, so then our overarching expected value is 1. It's a little bit more complicated, but not too bad for the expected value of x sub I times x sub j. So the probability of, so there's actually two cases. So given the case that the probability of x sub I times x sub j is equal to positive 1, we know that there are two cases in which that's true. It's true when x sub 1 is equal to x sub j is equal to positive 1, because positive 1 times positive 1 is positive 1, or it's the case that both are equal to negative 1, and negative 1 times negative 1 yields positive 1. So just kind of like plugging this in. If we're ORing the probability of two different things, we can simply add their respective probabilities. And if we want the probability that x sub I is equal to x sub j is equal to 1, well, we need the probability that x sub I is equal to 1, and then we can multiply that by the probability that x sub j is equal to 1. Repeat a similar process for there, and this is half times half is 1/4. This is half times half is 1/4. So we have a 1/2 chance. And by similar logic, we know that if the probability of x sub j is equal to negative 1 is 1/2. Because if it's equal to positive 1, then it's 1/2. So it's equal to negative 1, then it's also 1/2. And then we can simply sum up these probabilities, and we'll get 0. And now that we've found this term and this term, we can substitute it back into this final equation over here to simply just get a 0, so this canceled out, and then 1 for a sum from 1 through n. So we simply just get n, right? So in this case, the expected value of the square of the position of the particle after n moves is equal to n. Okay, so that's the variance, I believe. And we can view this as the measure of spread of the data, like from the mean, the expectation. So yeah, the variance definition goes as follows. For some random variable x with expectation e of x is equal to mu, this Greek letter is mu, the variance of x is defined to be the expectation of x minus the expectation of x, or the mean, squared. So, and then the square root of the variance is the standard deviation. So essentially what this is the measure of the expected squared distance from the mean. Okay. We're going to introduce another definition that follows from this, which just makes proving subsequent theorems easier. So for some random variable x, we're going to define e of x as mu again. We're going to show that the variance of x is equal to the expectation of x squared minus the expectation of x squared, if that makes sense. It's equal to this final expression right here. So, you know, just kind of taking the above equation, this one right here, we're going to multiply it out, then use the linearity of expectation to kind of distribute that, and then e of x is equal to mu, so 2 times mu is equal to 2 mu squared, so minus 2 mu squared plus mu squared is equal to minus mu squared. So this is equal to this is equal to this. Okay, hope you can see my, I'm assuming you can see my curve. Yeah, okay, anyways. So just another property, if we have a constant in here, we can just take out the constant squared, again, because the variance has this term squared. So yeah, I guess that sort of makes sense. Let's just go on to the computation for some simple examples, or relatively simple examples. So we have the expectation, so we want to find the variance, right? So the first thing we're going to do is calculate the expectation of our event squared, and what that looks like is it's basically the sum of each value in the range of x squared times its probability, right? So this is what we get, and we already know the expected value of x, so we can just square that, and this will get us our variance. Okay, and they didn't really prove these or write out the proofs, but I think we have the tools to do this, although I'm not gonna do it. So we have so random variable x on the set 1 through n, and x is going to take on values 1 through n, each with a 1/nth probability of landing on one of those values. So just to sort of define some things, the expectation of x is n plus 1 divided by 2. You know, you can use something similar to this to calculate, well, this without the squares. And then the variance is like that, and then the standard deviation is like that. So because this is this and this is this, that means that, like, by logic, that this is like, it's like proven. So okay, okay, for fixed points of permutations, so we're gonna let some event x sub n be the number of fixed points in random permutations of n homeworks. So if we want to find the variance, again, we have to calculate the expectation of the event squared, or the random variable squared, and we can also recall that that random variable is equal to the sum of a bunch of indicator random variables, where, you know, capital I sub I is equal to 1 if the student received their homework, and it's equal to 0 if they did not. So that sort of takes the same form as what we had above, which is like this thing. And yeah, that means that for each individual indicator event, the expected value of that is going to be simply just the probability that the student received their homework, which is a 1/n chance. And then let's see, we also again have to calculate this, so that's equal to the probability that both some student I and some greater student J is equal to 1, which is the probability that both are equal to 1, so this and this. So both are fixed points. So basically what this is saying is that there's a 1/nth chance that 1 is fixed, and given that one of them is already fixed, then there's a 1/n minus 1 chance that the second one is also fixed. So our total probability is this. And then you could just like do the math, and basically the expected value of x sub n squared is equal to 2. So the variance and mean are independent of n. That's something we just sort of have to notice from this. And so what is this really saying, this expected value? Like our spread, I think our expected value is just 1, no matter the size of the number of, like the size of the set of students. And then even the spread is only 2. So if n is super big, it's unlikely that there will be more than a few fixed points, because again, the spread is not very much. Okay, so next we're going to talk about the sum of independent random variables. So let's say x is the sum of a bunch of independent random variables. Then the variance of x is just going to be equal to the sum of the variances of each individual xi. And essentially, that's just going to total to the number of independent random variables times the variance of just one of those independent random variables. And then the standard deviation is going to follow similar logic, and so is the expected value. Okay. Yeah, I'm not really going to go like dissect through that, but let's see. I guess we're going to use this to show something else. So first off, for independent random variables x and y, the expectation of x times y is equal to the expectation of x times the expectation of y. So we sort of just use the expectation definition to come up with this. So for all a and for all b, we just take like a and b, we multiply it by the probabilities. So again, it's just like the range of x and y and the probabilities of x at a and y at b. But we can notice that if we know the probability of some b in y, that's not really going to influence the probability of some a in x. So we can just take the probabilities and multiply them like separately, if that makes sense. And then again, x is only affected by these a's, and then b is only really affected, or sorry, y is only like dependent on these b's, right? So we can sort of just separate out the summations like so, and then this takes the form of just the expectation of x, and then this takes the form of the expectation of y. So it's kind of because they follow from the fact that both random variables are independent. So using this, we're just going to comb through this, which is actually not too bad. So for independent random variables x and y, the variance of x plus y is equal to the variance of x plus the variance of y. So again, we're going to use the alternate definition of variance. that we defined above. And it's just it's just algebra at this point. So x plus y squared, this becomes these terms, and then using the linearity of expectation, we can just distribute the expectation, this like e, onto each term. And similarly, let's see. So we can distribute e of x to here and then e of y, and then take the sum of that and square that. So now that we have it in this form, we can simply just, again, multiply it out, and you're going to see that we have an e of x times e of x term, which gets grouped with this term right here. And then we have an e of y times e of y term, which gets grouped with this term right here. And then left over is the e of x, e of y, and then again e of x, e of y. So there's two of those, and again there's also two of these. So notice how this term right here takes the form of the variance of x, this term of here takes the form of the variance of y, and then this term right here actually just becomes 0, because this above equation right here states that the expectation of x times y is equal to the expectation of x times the expectation of y. So if they subtract each other, they become 0. And this is, it's important to note that in both, what are these theorems? I guess I will call them theorems. I don't know if they're... and we already stated this, but x and y are independent. This does not hold if they are not independent. So we're going to kind of look at the coin toss example. We're going to say x sub n is just the number of heads in a given n coin tosses, and we're going to let x sub n equal the sum of all of those indicator random variables, where if it's equal to 1, then we have obtained heads. Otherwise, if it's 0, then we got tails. We have to remember that all of these are independent, and so we can treat the expectation of x sub n as the sum of all of these independent variables. And we'll see that that actually totals to n times p, which we sort of already know. So if we wanted to calculate the variance, just follow the alternate form. If the indicator variable is squared, 1 squared is still 1 and 0 squared is still 0, so we still obtain p for the expectation of any particular indicator variable. And then if we're just squaring p, then it's p squared, and so we obtain this form. That means the variance is equal to np times 1 minus p. So that means if we toss, I feel like we've already talked about this a little bit, but if we toss a fair coin n times, with the probability of it landing on heads being 1/2, then the expected number of heads is n times 1/2. And then the standard deviation would take this form. Yeah. Okay, so really briefly, we're going to talk about covariance and correlation. I didn't really do the last part of the proof for correlation because I just didn't feel like it, so I just encourage you to look at the notes for that. It's not really bad, it's just... Anyways, so covariance, the measure of association between two events x and y, or that's something that it kind of tells us about. So as you can see, I just ripped these straight from the notes. The covariance of random variables x and y, denoted by this, is just defined as the expectation of x minus its mean, and then y minus its mean. which actually comes out to this equation, which we sort of saw above. And they don't really derive it, but they do give us some important information about it, which is that if x and y are independent, then their covariance is 0. But the converse is not true. And then if we have the converse of, or sorry, not converse, the covariance of two of the same events is just equal to the regular variance of one event. And then I don't really want to look through this last one, so I'm not going to. Let's see. I mean, this equation, like, that's there, that works. I don't know why this looks so funny, but I think, okay, so the sign of the covariance of x and y tells us how much x and y are associated, I guess. And then briefly, correlation, just to sort of spit out what it is. X and y are random variables, and we're going to say the standard deviation of x is greater than 0, and the standard deviation of y is greater than 0. If that's the case, then the correlation of x and y is defined as the covariance of x and y over the standard deviation of x times the standard deviation of y. And the correlation always ranges between -1 and +1. I guess that just makes it easier for us to work with. So I feel like this wasn't one of my better notes, but hopefully I just sort of like gave some sort of help on some of these topics in this note. But yep, this has been note 16, variance and covariance. Alright.